Right. Hello, students. I'm Bob Burke, and we're going to go through a very high-level presentation on cryptography and hashing. The intent of this presentation is to give new students an insight into the data that they might see in the system, data that is in transit, data that is at rest, or data that's being processed. Um, some of that data might be encrypted data or cryptography or hashed data. So today we'll focus in on those types of data elements and what to do with it. Uh, we could spend a week on these topics. They're very broad and very deep. We're just going to look at some of the high level concepts and some of the formatting things you might see so you're familiar with it and you may know how it helps you understand how to handle the data. Let's get started. Cryptography is one of the skill sets that we're working on as part of our cybersecurity skill development. We'll talk about cryptography, encryption, and hashing today. A little bit about password cracking because hashes are used for storing password information. Very little on that. Encryption. So the basic concepts here are encryption has a plain text message or a source message that is then encrypted using some sort of an algorithm and a key, and you come up with ciphertext. So you go from plain text, you encrypt it, and you have ciphertext. That ciphertext is oftentimes what is stored or transmitted to other users, other systems, and so on. On the hashing side, hashing is different than encryption in that it is used to protect the integrity of the file. A hash is generated on an existing source file, so you get a new string of characters or new data, and it is used to verify the integrity of that source file. So should that source file be changed for any reason, and then you run your algorithm, the hash values would also change, and it's a quick way to detect has something changed in the source file. Key concept we want to tie this back to is encryption is used to maintain secrecy, keep information secret, so that is tied to confidentiality. Hashing, on the other hand, is used to ensure integrity or validate the integrity of data. So that's tied to the integrity of the CIA Triad. The only other thing we will mention, not related to CIA, but with encryption, modern encryption, we have the ability to do digital signatures and things of that sort, certificates. That also helps with authentication, which is another element of managing the identity or verifying the identity of who's using it, what they're authorized to do, and how we generate accounting information of what they did. Classical cryptography. Well, we break cryptography into two major groups. Classical, and this is pre-computers, back in the ancient days of Rome, Greece, Asia, Africa, all civilizations. Before there were computers, they had to find ways to keep information secret. One good thing, at least, was few people read. So oftentimes information could be almost in plain sight and you just had to do minor things to even confuse the few people who were able to read it. There are two groups under classical cryptography. There are substitution type ciphers and there are transposition type ciphers. Substitution ciphers basically take the letters in the message and substitute them out with other letters. So you are going to replace every letter in your message with something else. Transposition, on the other hand, is all the letters of your message are in your message, but they have been rearranged, reordered. They're in a sequence that doesn't make sense. So the existing letters then are reordered in such a way that it creates a message. That's transposition. Modern cryptography, there are two groups we'll talk about a bit more later, and there's symmetric, and that one is where we have cryptography where both the encoding and decoding of the message use the same key. We share a single key, so we have to be careful on how we manage that key, and that key doesn't get into the wrong hands. Asymmetric, on the other hand, uses a public key infrastructure where data is encoded with a public key and decoded with a private or secret key that only the end user has, their secret key. Everybody has their own secret key. That way we can ensure secrecy. It's better security. It is more expensive and it takes more time, but it allows, especially in our new internet connected world, us to maintain secrecy amongst many, many users. In the classical cryptography, again, this is before we had computers, some very simple techniques were employed. For example, shift ciphers, Caesar and ROT13, which stands for rotation 13, are basically where you're taking the letters in your cipher message and shift them 3 positions, 5 positions, 13 positions, and look for the corresponding letter in the alphabet. For example, an A becomes a D, a B becomes an E, a C becomes an F, if we do a simple shift. Okay. There are other ciphers. I'm not going to go into them in detail. You can read up on your own, but I put a list here. These are ones that are very popular in cyber competitions. They're fairly simple or not so simple, but if you run into a competition, you get some cipher text, you may want to go down this list: cipher, ROT13, AZ, A1Z26, and so on. Transposition ciphers, again, that's where all the letters are there, but they have to be rearranged. And here are a couple of examples of transposition. The comment I do want to make on this page is if you have a lot of cipher text, a lot of data, you can use a tool to run a frequency analysis because we know certain letters are more popular than other letters. For example, E, R, S, T are the most popular letters in the alphabet. So a frequency analysis might take the ciphertext and say, hey, although you have an X, you have it as the most frequently used letter, so it's probably an E, and so on. Okay, I'm going to pause here and say, when you get these messages, you're going to have to do some trial and error, but these, for example, are some of the most popular ciphers that are used. You may want to try these using decoding tools. Moving on to modern cryptography, a very, very difficult to decode these if you don't have the key. Again, symmetric encryption is meant to be decoded. The keys are shared, so the challenge is to make sure the keys don't get into the wrong hand. Symmetric encryption is faster than asymmetric encryption and cheaper to use. Asymmetric encryption, on the other hand, uses a public key and the user has their own private key. It is more secure. It allows you to do things like digital signatures and have signing certificates and things like that that help authenticate the end user in who's receiving or decoding the data. So those are two modern. You're not going to see these on cyber competitions normally unless it's more advanced. Switching to hashing. Hashing, again, is a way of checking the integrity, verifying the integrity of a file. It is a long string of characters that are generated by an algorithm. The algorithm is a one-way algorithm. It is not reversible. So there's no way to go from the answer back to the source data. They also add random characters, which we call salt. Random characters are added to the hash to make it even more difficult to figure out what was the source. How did we get to this hash? It's used to identify files, to verify files have not been changed, and to store data, sensitive data like passwords. There are tools that can be used to help generate, identify hashes. There are a few tools that'll help you crack a hash, primarily if that hash is in a repository or a dictionary of cracked hashes. You can use something like Online Crack Station to see if it is already on a list of compromised hashes, and if so, you might get a hit. Okay. Now, decoding. So we talked about this briefly. Encrypted data is meant to be decoded. So as long as you have the text, the ciphertext, the algorithm, you know, and you have the keys, you can easily decrypt that data. If you have two of those, sometimes you can, through trial and error and multiple iterations and the power of the computer, sometimes try many different examples and still decrypt the data, depending upon how complex the algorithm is. On hashes, as we said before, these are one-way formulas, very difficult to crack. And pretty much the only way to crack one is if you have a dictionary or a word list of compromised hashes to compare it to. Those are called rainbow tables. But there are tools, and we put a couple links here that are used to brute force attack, try countless iterations and variations of hashes that have been compromised to see if we can get a hit. Okay, we're up to the summary. We've touched these points before. What encrypted data is, it's tied to confidentiality. We talked about classic ciphers and modern algorithms, and that that at least encrypted data is meant to be decoded as long as you have the key. Hashing is about integrity, and we just covered the one-way algorithms, not reversible. And the only way to really figure or decode a hash is if it is included in a list, a word list or dictionary of compromised hashes, otherwise called rainbow tables. So we are near the end of the presentation. At the back of the presentation, we have a page of ciphers. These are classical ciphers. You'll see the ciphertext on the left. On the right are links to tools, decoding tools. We'd like you to give a try and practice. And once you practice, you'll start to see some, if you will, patterns that may help you recognize the data. I do show the list on the right. These are very popular in competitions: A1Z26, @bash, Shift or ROT13 type ciphers, rail fence ciphers, Veneer. These are all very popular, but there are others. Then finally, we have another page at the back of the presentation on hashes. These are some examples of hashes that go out and crack. The good news is you don't have to hunt, peck, and cut and paste each one of these individually. You can take all the hashes on this example list, cut them out as a block, and put them in a tool like CrackStation. Put them all in there. Let them know you're not a robot. Click submit, and it'll crack each and every one of them. It'll tell you what kind of hash it is, if it has it in its word list, and it'll tell you what the associated passwords are. So give it a try. Not all of them will crack. The ones that don't crack, I'd like you to go look at Hash Analyzer. But anything you can't crack in CrackStation, put it in Hash Analyzer and see exactly what kind of hash that is. And that can be useful information too. So with that, class, that concludes this walkthrough. Send me an email, text me, contact me if you have any questions, and I'll see you in the next video. Bye-bye.